First of all, I would like to thank Jose Miguel, who is not... I wanted to thank Jose Miguel for organizing this nice meeting and also for inviting me to give a talk. So today I'm going to be talking mainly about imaging observations of luminous and ultraluminous infrared galaxies. And in particular, I would like to highlight Tanio Diaz-Santos' name because he was my former student, grad student, and he's done a lot of the work that I'm presenting here today. So, of course, we knew about the existence of infrared bright galaxies for a long time, from the early 70s, but it was really with the IRA satellite that we started discovering them in large numbers. So we came up with not we, but people came up with a very simple classification in terms of the total infrared luminosity. So if a galaxy has an infrared luminosity between 10 to the 11 and 10 to the 12 solar luminosities is called a lurk, and if the luminosity is above 10 to the 12, it's called a U-lurk. Then people classify them in terms of their iris colors. So if the 25 micron to 60 flux ratio was less than 0.2, they were called cool, you should say cool, not cold, cool lurks or U-lurks. And then this type of galaxies tend to be dominated by star formation. And then if a galaxy has a ratio of 25 to 60 microns greater than 0.2, they are called warm lurks and U-lurks. And then they tend to host an AGN. This doesn't necessarily mean that the AGN dominates the bolometric luminosity, but also what happens here, this is difficult to see, here basically we have the infrared luminosity increasing this way, and it's just showing you the AGN fraction in black with these cipher 1s and these hashed in this direction are cipher 2s and then liners. So as the infrared luminosity of the system increases, the AGN fraction increases. The other main property of these luminous and ultraluminous galaxies, of course, is that they emit most of their energy in the infrared range. That's obviously how they were selected. So what happens is that a large fraction of their UV and optical emission gets absorbed by dust, and then it gets re-emitted in the infrared. And this, because there is so much dust, it also is clear that they have very high extinctions, and they can be as high as 100 magnitudes. And also to remark that the dust can be heated by both, obviously, AGN and star formation. In the local universe, lurks and U-lurks are a very small fraction of the galaxy population. But we know now, first with the ISO surface and now with Spitzer, that lurks and U-lurks are very common at high redshift. I'm just showing here two different graphs. This is from Pablo Pérez González using early Spitzer data. And what you can see here, this is the infrared luminosity versus the redshift. And as you can see, galaxies above this line here would be classified as lurks, and above this line here would be classified as U-lurks. And as you can see, at redshift higher than 1, you're mainly dominated by this population of lurks and U-lurks. And what is also interesting is that if you look at this Maddow plot, so this is the co-moving star formation rate density of the universe, and this is going from 0 to 1. Of course, we have, now we know out to redshift 4 or so. But what you can see is that, in the local universe, the contribution from lurks and U-lurks is very small. But as you go to redshift 1, you can see that lurks, shown here in yellow, dominate the star formation rate of the universe. And then as you increase to larger redshifts, what happens is at redshift 2, lurks and U-lurks have equal contributions, more or less. And then at higher redshifts, they are dominated by U-lurks and 2-millimeter galaxies. So, of course, now there's a great interest in understanding these high redshift lurks and U-lurks. And in particular, I think there has been a very interesting result very recently, which is that if you study some of these most luminous objects at redshift 2, which are in terms of their luminosity, they are like U-lurks or even hyperluminous. So with infrared luminosity, it's about 10 to the 13. They took a spectra, and here is the blue line. With the shaded is the 1 sigma dispersion. So this is the average of about 20 U-lurks at redshift 2. This was done with IRS on Spitzer. So if you look at the, of course you can't see much of the slides, but what is interesting is that in terms of their mid-infrared spectra, they look more like lurks than local starbursts, not like local U-lurks. A local U-lurk would have a very deep silicate feature. And here I just plotted, I don't think you can see it in green. So basically it's clear that there is something happening at high redshift that is not quite like in local U-lurks, where what happens is that the star formation or the AGN, all the activity is very concentrated in the nuclear region. And here you can see this is a compilation by Lee Armus of U-lurks in the local universe. Of course, there is a variety of mid-infrared spectra, but most U-lurks in the local universe, as you can see, they have very, very deep silicate feature, pHs, etc. And the ones that are dominated by AGN, like these ones here, they tend to have almost featureless spectra. And in contrast, what you see when you look at local lurks, you see that most of them just have relatively moderate silicate features. I mean, still pretty deep, but not as deep as U-lurks. So one of the explanations for what's happening at high redshift is that maybe the star formation at high redshift is not happening in very small regions. It may be happening all over the galaxy, maybe with some regions that are very obscured, but other regions of moderate optical depth. So in that respect, I think it's very interesting to study local lurks, because the star formation processes taking place locally in lurks may resemble those happening at high redshift. So in the past, there hasn't been too many mid-infrared imaging studies of local lurks. And most of the studies were done with Keck a few years ago by the Seufer group. But they mainly concentrated on lurks and U-lurks, but they usually study the most famous objects and in general the most luminous ones. So here I'm just showing an example, ARP-299, which is a very famous lurk. It's an interesting galaxy. And one of the results they got from their study is that they found that in general the mid-infrared emission was very concentrated in a number of regions in this galaxy. But mostly, most of the emission is coming from the central parsec, the central kiloparsec in each of these two galaxies. So now what we've done is, of course, I mean, ARP-299 is almost a U-lurk, so maybe it's not very representative of the luminous infrared class. So what we did, we selected from the IRAS revised bright galaxy sample, which is just based on the IRAS data. From this large sample, we selected a sample of lurks. So basically, we just set the infrared luminosity to be between 10 to the 11 and 10 to the 12. And then the first thing we wanted to do was to observe them using the Paschen alpha emission line in the near infrared. Why we wanted to use Paschen alpha instead of H alpha, for instance, is because the extinction gets greatly reduced in the near infrared. So since we know from optical spectroscopy that these galaxies have relatively high extinctions, you want to study them in the near or the mid-infrared. So basically from this large sample, we just limited our sample in volume, so we could actually observe them in Paschen alpha using one of the NICMOS narrowband filters. So that's the only restriction, is just the distance. So we came up with a sample of about 30 lurks, and it's representative of the lurk class in terms of the AGN fraction, which is about 30%, and also the morphologies. In general, in lurks, maybe some misconception for a lot of people, lurks are not dominated by interesting systems. They are mostly spiral galaxies or galaxies in groups, minor interactions, and it's only about 1/4 of lurks that are in strongly interesting systems or mergers. So, as I said before, this sample is representative of the properties of lurks in general. So what we did, thanks to Chris, we took observations with T-Rex on the Gemini South telescope. And so that's how we started this collaboration. So one thing that I want to show you here is something that is not appreciated by a lot of people, is the comparison between IRAC observations on Spitzers, and these are the IRAC images at 8 microns, and what you can get with T-Rex on an 8 or 10 meter class telescope. So you can see here the 8 micron images taken with IRAC of a few of our galaxies. And now the same galaxy seen by T-Rex. I mean, you can see, I mean, the change in angular resolution is amazing. You gain about a factor of 10 in angular resolution just because of the size of the telescope. Of course, Spitzer is much more sensitive, but these galaxies are very bright, so it's relatively easy to observe them from the ground. And just to give you some numbers, at a typical distance of 50 megaparsecs, with Spitzer, your angular resolution depends on the wavelength, of course, so it's between 2 and 5 arcseconds. And this converts into physical sizes of between half and 1 kiloparsec. If you study the same kind of galaxy with a CanariCam, and then your diffraction limited, and I think I'm using the Gemini number, so it's slightly better than that, then you can get to typical angular physical sizes of tens of parsecs. So while with Spitzer, maybe you can look at structures on large scales, with CanariCam and T-Rex, you can get a structure that allows you to really separate the nuclear emission from the H2 regions. And also, just to give some numbers, maybe useful, we were typically, for imaging, we were using 15 minutes on source. And we were able to get to fluxes of 0.5 millijanskis, sort of on average for H2 regions. So obviously, you can get fainter than that. But just getting this kind of fluxes was very easy. So just to convince people that you can do extragalactic science from the ground. And you can look not only at the nuclei, but you can look at H2 regions. So one thing that you can see here, this is a comparison of our NICMOS images and the T-Rex images. That's something that Paco told us yesterday. With T-Rex and CanariCam, you get angular resolutions that are comparable to the HSP resolutions with NICMOS. So this is very nice in terms of comparing the different physical processes. So here what we can see is that when you look at the near-infrared continuum of LERCs, but this is general to any kind of galaxy, the near-infrared continuum is mostly tracing the more evolved stellar populations. And then when you look at Persian alpha and the mid-infrared continuum, you see that the morphologies are quite similar. And they are telling us that the mid-infrared continuum is mostly tracing the young ionizing stellar populations. And the other interesting result that we've published in these two papers here is that in LERCs, the mid-infrared emission is not only in the central kiloparsec. I mean, it can be extended over 5, 6, 7 kiloparsecs. So you get emission not only from the nuclei, but also from bright H2 regions in the spiralams. And this is not what you see in ULERCs. What you would see is that most of the emission would just come from the central kiloparsec. So in that regard, LERCs are not very similar to ULERCs. And just to give you some numbers here, in the nuclei of the LERCs that are dominated by star formation, we measure sizes, physical sizes of between 50 and 200 parsecs. And also what is interesting is that to point out here is that the nuclear infrared emission accounts only for a small fraction of the total luminosity of the system. So usually we find that it's between 10 and 50% depending on the galaxy, whereas as I said before, in ULERCs, it tends to account for almost 100% of the luminosity. You get very high infrared surface brightnesses, and of course you can see here the numbers here. This is a compilation by Seufer et al. From 2001. But what you can see is that the nuclear surface brightnesses are comparable, of LERCs are comparable to the core of Orion. So obviously that is telling us that the processes taking place there are very, very energetic. Then when you look at the nuclei of the AGN, of course what we find is that the mid-infrared is mostly unresolved. But in some cases we detected extended emission, which is telling us that there is probably some nuclear star formation taking place in scales quite close to the black hole. In the cases of AGN, they maybe contribute a little bit more to the total infrared of the luminosity, but again, they don't dominate the infrared luminosity of the systems. And of course, this is not surprising. The infrared surface brightnesses tend to be higher in AGN than nuclei dominated by star formation. And here, just to show you this is one of the galaxies in our sample. Here is just a composite of 4 HSP filters, and here in Persian alpha in this plot is in magenta, which is equivalent to the mid-infrared. Okay, So you can see that I mean, these systems are incredibly dusty and complicated, and they are, they have a lot of H2 regions and star clusters. So obviously, there's a lot of stuff going on there. Also, here's just the summary of some of the properties that we have been finding in the H2 regions and star clusters, etc. But also the interesting thing is because the star formation rates of these lurks and ULurks are very high, and it's something I didn't mention before. They are between 10 and 1,000 solar masses per year. It is expected that you will have a lot of supernovae exploding in these systems. And just to give you just a little bit of publicity for something we did with, we did it in the near infrared, but with Gemini, we detected a supernova in one of our galaxies, and we are trying to monitor a number of galaxies just to see if we really detect as many supernovas as we are predicting. So one thing, I'm probably just going to skip this one. So one thing that, so of course, one of the goals of this work was to understand what's producing the mid-infrared continuum in this kind of galaxies. So we saw before that the morphology with Paschen alpha is similar. The two morphologies are quite similar, so maybe you can use the mid-infrared continuum as a star formation rate indicator. Now, why bother if you can use H alpha or Paschen alpha? That is probably easier to use. Well, at high redshift, most of these galaxies are going to be very obscured. So you want to get a star formation rate indicator that is not affected by extinction. So this is work done by Daniela Calzetti and collaborators. So why are we interested in calibrating the 8-micron luminosity? Well, at redshift 2, if you observe a galaxy with MIPS at 24 microns, that corresponds to red frame 8 microns. So people have been putting a lot of effort into calibrating the 8-micron luminosity versus the Paschen alpha luminosity. And here, these are H2 regions in the Sphinx sample, which are just nearby relatively normal galaxies. And you can see that there is a very strong dependence of this relation with the metallicity. Low metallicity H2 regions tend to have lower, for a given Paschen alpha luminosity, they have lower 8 micron. This is with a broadband filter, so you're not only looking at hot dash continuum, and this filter also has pHs. So what's happening, and I think what we know now from spectroscopy of low luminosity, low metallicity galaxies is that they tend to have faint pH emission. So at least for the low and intermediate metallicity galaxies, we kind of understand what's happening here, and it's telling us that you have to be careful. You have to know the metallicity of your galaxy, or to have an idea at high redshift if you want to use one of these relations. But even looking at the high metallicity galaxies, there is a lot of dispersion in this relationship. So what we did is with our T-Rex imaging data, we looked at this relationship not only on the scales that they were doing with Spitzer, that it was about 500 parsecs in diameter, as you can see here. Their apertures were too big. I mean, they couldn't isolate individual H2 regions. So what we wanted to do with T-Rex is to take advantage of the really good spatial resolution that we can get and just use much smaller apertures and see if that relation between the 8 micron and the Paschen alpha luminosity is held or not. And what we found is, yeah, I mean, you do see a relatively good trend, but there is a lot of scatter. So we were able to explain this in terms of the age of the stellar population and also the contribution from the pHs. So what happens is, what we think we understand is when for the equivalent width of a Paschen alpha or H alpha, whatever hydrogen recombination line you want to use, it just gives you an idea of the age of the ionizing stellar populations. So here is young and here is old, but I mean only millions of years. So this would be about 2 or 3 million years. Here is about 8 million years. So this is only the ionizing stellar populations. And what we can see is that in young H2 regions, you have a deficit of 8 micron emission. And we don't know why that is happening. We don't know if the pHs are being destroyed because the ionizing, the radiation field is very harsh. But obviously, I mean, this trend is very clear. And even at a given age, you also have this scatter in the vertical direction, which is telling you that the pH features maybe change from galaxy to galaxy. And they can, and other studies are finding now that they can vary by a factor of 10. So the main conclusion from this work that we did using very good spatial resolution is that if you want to calibrate the star formation rate in terms of the 8-micron luminosity, you really need to do it with the integrated properties of galaxies. If you go region by region, you're subject to these kind of variations. And if you want to have a good calibration, you just have to take the integrated luminosity and just hope for the best. Because I don't think in general the pHs are not very good calibrators of the star formation rate, but that's maybe because they are so bright at high redshift, that's what you're going to be getting. And just very, very quickly, so what's next for infrared bright galaxies? Of course, we've done a lot of work with T-Rex. However, I think that we really need to do a lot of work using spectroscopy. This is just observations of, again, ARP 299, which is an interesting galaxy. And this is IRS spectroscopy done with apertures that are of the order of 4 seconds. I mean, that's the best you can do with Spitzer. And in this galaxy, because all the components are well separated, we were able to separate them. And here I'm just showing you all the features that you can get from the ground. So you can look at pHs, the neon 2 line, which is a very good indicator of the star formation rate. You can look at the silicate feature, the argon 3 line, the sulfur 4 lines. So obviously what we want to do is to actually look at all these features on the scales, as I said, of tens of parsecs rather than kiloparsec scale. And we've done some preliminary work for 4 lurks, but obviously our hope is that we are going to be able to study a lot more with CanariCam and really not look at the famous, of course, not look only at the famous galaxies and the most luminous galaxies, but really look at the properties of lurks covering the full range in infrared luminosity. And just to finish, just to put up my conclusions, I think that's what you need to take away from this talk. I mean, in terms of angular resolution, I mean, there is no comparison between what you get from IRAC and what you can get from the ground. Okay? Yeah, Spitzer is very sensitive, but we will have to wait until MIRI on JW2 to get this kind of spatial resolutions from space. And that's all. Thank you. Mm-hmm.
And you put up the T-Rex kind of spectra, and you blank out the kind of below 7 microns, above 15 or above 13 microns. How important do you think the 5 microns and 3.5 micron window would be, the LNM bands?
Well, in terms of, I mean, probably you're only talking about imaging. I mean, spectroscopy would be. Oh, I think spectroscopy would be fantastic. I mean, the problem is that, here in this spectral range is very difficult to know where the continuum is. It's almost impossible. If you have a source that is dominated by a pH emission, like the red line here, just having this from the ground, really, you have no idea what the continuum is. Of course, if you have some photometric points here you don't have as many features. So if you have a photometric point at 5 microns and at 3 microns, it's a lot easier to really know where the continuum is. And for instance, if you want to measure the silicate feature, the depth of the silicate feature, or even just getting good fluxes for your lines. And then, of course, spectroscopy is even better. You have other pH feature at 3 microns, so it would be extremely useful. Well, yes. So in this paper, of course, yeah, we did that, and we just problem. I mean, and Nancy will tell us all about the silicate feature. I mean, it's very complicated. You have to know the geometry of your source. What we did in this paper is just we assume the usual easy, just the screen, and yeah, you can convert the depth of the silicate feature into an optical magnitude. And yeah, in this kind of, for instance, this very embedded nucleus, you get about 30 magnitudes. But I don't think that's the real number. It's just to give you an idea. Even the ones that don't look to be, very deep, I mean, you still get like about 10 magnitudes of extinction, just without, just assuming a very simple geometry. So, but I think Nancy's going to tell us all about it. Yeah, but I think in relative, I think it's good to see in relative terms, obviously. Yeah. That's going to be, much more expensive, and yeah. But it's not a simple thing to do. That's what I have to say. I'm not sure. Amorphous, yeah, I mean. Yeah. Right. Oh yeah, no, that's what we've been doing. But that you're assuming you have just a screen of dust, and yeah, I mean, and you assume one of the extinction laws, and yeah. But there hasn't been any. I don't think the Spitzer spectra were good enough to do that kind of composition analysis. That's something that probably will be done much better with MIRI, because you have much better spectral resolution. You can figure out what kind of silicates you have? Oh, okay. Yeah, and which... Right. And LERCs, I mean, if your silicate feature is not very deep, I mean, I think it would be difficult, right, for some of the LERCs, just because the 18 micron feature is not very deep at all. So, okay, thanks.
Let me put this on while it thinks.